Hello, everyone. Thank you for getting up so early for my talk. I'm guessing it will be the coolest talk of the day, measured by the room temperature. So this is a work I done earlier this year with three wonderful PI guys. So when I was still a faculty at PI, so it's literally a PI collaboration. Ryan is a postdoc at PI. Zheng was a student at PI moving to Harvard, and Chong is faculty at PI. Okay, so today I want to talk about phase transitions, in particular phase transitions out of topological ordered phase, which we know that usually it's beyond the Landau paradigm. And let's be concrete. So let's pick the simplest topological order. That's the torical phase. And I'm sure that everyone in this room are familiar with this model. It's an exact solvable model, and the ground state is a deconfined phase of essentially the Z2 gauge theory. And we know that this theory has three types of gapped topological excitations. That's the Z2 gauge charge E, the Z2 gauge flux M, and their composite. And the particular interesting thing in this deconfined phase is that the E and M particle has a non-trivial mutual braiding. That there's a statistical phase of -1 when you break one around together. And because of that, their composition here becomes a self boson. And what's most relevant and interesting for this talk is that this model secretly has an interesting symmetry that's exchange the E and M particles. This symmetry actually you can realize on the lattice in many different ways. For example, the simplest is do a translation along the diagonal direction that we realize as a microscopic Z symmetry. And you can also realize it as Z2 symmetry by some finite depth circuit, and either Z2 or Z4, or even you can do a pi rotation around the center, connecting between each plaquette and vertex. And then that will be realized as a Z2 symmetry that's not unsightable. But in the end, as an IR symmetry, it will all run into a phase 4 Z2 self-duality symmetry. So that'll be our focus today. And then given this topological phase, you can turn on perturbations. Basically, you turn on the fluctuations of these gap excitations. Then you can tune your Hamiltonian out of this topological order phase. For example, the thing you can do is turn on the fluctuation of this gauge charge. And then there's this historical phase transition that runs into so the Z2 particle, the Z2 gauge particle will run into a Higgs transition into a trivial phase without any topological orders. And this model has been studied for almost half a century, I guess, and is known to be an Ising star transition. Or in other words, it's the Ising CFT coupled to a Z2 gauge theory. Nowadays, you will also can call it gauge Ising CFT. And physically, it's literally that the gap of this E excitation become closed, become massless, and that drives this Higgs transition. And to connect with the Lagrange in anion unities, it's also called E-anion condensation. And then you can apply that EM exchange symmetry. You will get a different model where now it's the M particle, the Z2 flux, going to fluctuate and drive them. And since it's coming from this exact mapping microscopically, so you know that the transition will be still in the same time. It's still the Ising star transition. And in this time, we call it the M-anion condensation. But more generally, of course, you can tune on more perturbations. In particular, you can turn on both the fluctuation and E particle and M particle. Then you will have a 2D phase diagram. And along the two axes, we know that along the two axes is the Ising star transition we have talked about. And if you run the RG, you will find that this whole line here it will flow to this point, and it's still an Ising star transition. And similarly, by applying this self-duality symmetry, you'll find this line is also an Ising star transition. So we know all about the space diagram except along this self-dual line where the fluctuation of E and M is an equal weight. So the mystery is what happened along this line. And indeed, it's people have done a lot of numerics on this problem. And the first numeric is done by Kitai and collaborators in 2008. And they found that there's a deconfined phase will connect to a first order transition line. So this black line here is a first order transition line where the Z2 self-duality symmetry along this line is spontaneously broken. So it's almost a degeneracy of the E condensate and the M condensate. And they couldn't tell what happens exactly at this near this point. And since then, there's a lot of numerics, and it is really Adam Nasu's numerics in 2020 that they found compelling evidence that this is indeed a direct continuous transition connecting this deconfined phase and symmetry breaking phase. So they literally find the scaling invariance at this point and can extract the scaling dimensions of the perturbations that drive along the direction. So it's been numerically confirmed that there is a direct continuous transition that from this Z2 topological order phase to a trivial phase without any topological order. Nevertheless, the Z2 self-duality symmetry is spontaneously broken. So then this numerical results gives us such a theoretical challenge. What's the nature of this transition? Because you're naively, all the topological transitions can be considered as certain kind of anion condensation. But here, we don't have that picture anymore because E and M particle have mutual statistics. So they can never condense together. And because this is a first order transition, so actually they indeed not condense together. So how can we understand this phase transitions theoretically? And the more concrete questions is like, can we have a field theory that gives us at least a mean field level picture of this transition for this? And this field theory we're asking for has at least two natural properties. One, it can incorporate this 2 degree of freedoms with mutual statistics. And the second is it should naturally give a direct transition from this topological order phase to a global symmetry spontaneous broken phase. So this is the question of the day. So before I tell you the answer, let me tell you the intuition of how did we solve this problem, or the hints to solve this problem. So we use this tool that's familiar to this audience, I think. We're going to gauge this self-duality Z2 symmetry. As I said, even though this symmetry is it's kind of mysterious on the lattice, but as an IR symmetry, it's a very proper normal symmetries that we can properly gauge it. And it's also known that I think from the fracking in the 2015 that if you gauge this toric with this EM exchange symmetry, you will get this double Ising topological order. So each Ising has this sigma and Pasay as non-trivial anyons, and the bar is the time reversal pair of it. So once you gauge this EM exchange symmetry, you get a different topological order, another abelian topological order, and the most interesting you notice that this is on the horizontal lines is the transition we are focusing about. We know that a tuning along the self-field line, the gap of E and M will go to close simultaneously. They become gapless when you're approaching the critical points in the same way. And exactly by gauging this self-duality symmetry, it is the E and M that combine combines into a single non-abelian boson. That's what we usually call sigma bar, sigma bar. So it's a legitimate non-abelian boson in the gauge theory. And even though we have the problem that in the bottom lines, the E and M have mutual statistics, they can never condense together. On the top lines, we just have a normal ordinary self boson, even though it's non-abelian, but it still can condense. So on the top lines, the transition is very easy to understand. We're just tuning the gap of the sigma bar to be gasless. And once that transition, we can apply our ordinary anion condensation theory. And we know that the condensation, condensed algebra that contains sigma bar, there's only one of them, and that one also contains precipitate bar, which means that once you tune the mass of sigma bar to 0, the mass of precipitate bar will also go into 0. So this line of transition will give us a trivial confined phase that has no topological orders. And through this gauging, we know that we'll gauge a zero form symmetry. In the gauge theory, there will be an emergent one form symmetry. And indeed, along the top lines, we have a Z2 one form symmetry generated by the precipitate bar line. And since it is a confined phase, so this one form symmetry is still symmetric, it's unbroken. So now we can fill out the gap, fill out other parts. And we know that on this bottom, we will have a trivial phase. We expect from the numerics that it's a Z2 zero form symmetry and spontaneous symmetry breaking phase. And indeed, by the sanity check, you know that when you gauge this symmetry breaking phase, gauge the global symmetry in the symmetry breaking phase, we should get a confined phase where the Z2 one form symmetry is symmetric. So this diagram will work. So the upshot is we want a theory that secretly behind it is a non-abelian boson that's going to condense.
Gauge the one symmetry of the diploid force to get the force. Is that an exchange of isomizing?
No.
What is this?
It's just a precipitate bar line. Precipitate bar is a single self boson in this topological order. It's one form symmetry. It has some mutual statistics with sigma sig. So when this line lines around the sigma line, it will get some statistical phase. It's not a. It's a one form. It's no longer.
The first that form theory and your gauge. So you must get a force in event in the as bar. And once you is the actual force in the and expect it's just swap it twice.
No. Sorry. It's in 2D, so if you gauge a zero form symmetry of one form, we wouldn't exchange anions, because exchanging anions is zero forms.
Yeah.
Okay, this is the physical picture. Now let me tell you the answer. So my claim of the day is that this gauge theory will work to give us a perfect mean field understanding of this self-dual transition. And if you are like a field theory guy, you probably can read in the real time what's meaning here. So but let me explain here. So we have a gauge theory where the gauge group A is a SO4 gauge field, and it couples to a free scalar that's in the SO4 vector representation. So it's a 4-component real scalar. And this part is just some 5-4 terms, and so it's the ordinary. And this is the Yang-Mills terms. So if you forget about the last terms, this is just the ordinary SO4 Higgs transition. And but actually we have the last term, which is the topological term. So recall that the SO4 group can be written as 2 copies of SU2 and over a mod Z2. And let me call one of the SU2 the left one, the other the right one. And then I can write all the gauge fields in terms of left and right SU2 gauge fields, and the phi field will be the bifundamental under the 2 copies of SU2. And after that, This last term will be a transimus term, where this left SU2 gauge field will be put on in level 2, and the right SU2 will be put on in level -2 of the transimus theory. The whole theory is time reversal invariance. Any questions about this field theory? Okay, so before so the upshot is this field theory is just describing the Higgs transition of the SO4 gauge theory with the standard 5-4 term and Yang-Mills term, except now I add a specific transimus term. And I will from now on I will call this SO4 2, -2 transimus Higgs theory. This is indeed described a transimus Higgs transition. So before we try to go to the phase diagram, let me first check what's the global symmetries in this theory. So first is as a time reversal symmetry that swap the two transimus terms. So we will exchange the two SU2 fields, and then accordingly, when X on the phi field, it will be an improper Z2 rotation. And more interestingly, S actually has a strictly unitary Z2 symmetry that describes the Z2 flux conservation in this theory. So this is because the pi1 of SO4 is equals to Z2. So the charge operator will be the monopole of this SO4 gauge theory. And we care about this global symmetry because I will show you that this Z2 flux conservation symmetry will actually be our self-duality symmetry when acting on the low energy topological orders. So if you want to measure the conserved Z2 flux through a closed surface, we'll use W2. So there's a typo. It's a W2. It's the second Stiefel-Whitney class, and on the SO4 gauge theory, and it has a Z2 cascade. And if we want to expose the symmetry of this field theory, we will couple to background Z2 gauge fields. And for that, we will add additional topological additional terms to the theory, I pi and this background A, and cut product with W2, the Stiefel-Whitney class. Okay, that's the symmetry. So we are only field theory looks very unconventional, but it actually only have two discrete global symmetries, and so it has a very small emergent symmetry. So now let me try to tell you the phase diagram given by this theory. In particular, we will tune this mass term, phi square term, and I will show you that when the R is greater than 0, we will have the low energy will have a Z2 topological order, and in particular, this Z2 flux conservation symmetry will act as a self-duality symmetry that exchange the emergent E particle and M particle. And when the R is smaller than 0, the phase will be trivial. There's no topological orders. And I'll show you that this Z2 flux conservation symmetry will be spontaneously broken. That's our goal. So first, let's talk about the topological side. So when the mass term, when the mass is positive, the phi is gapped, so we can integrate out, and we are left with only the transimus term in the low energy, and I will call this a SO4 level 2, -2 transimus theory. So let me show you that this transimus theory actually describes torical phase. So the way to do it, we will use our trick to gauge the global global flux conservation symmetry. So let's first suppose that this gauge field A, it should be in SO4, but let's suppose first that it's in the SU2 times SU2. Then because we have only this level 2 and -2 for each of the SU2, this transimus theory is familiar to everyone. It has the left part has 0, spin 1/2, and spin 1 representations, and the right one has also the same. And actually, this transaminase theory it's very similar to the double Ising theory. And using this Kitai's table, you know that SU2 level 2 is a cousin of the Ising topological order. Basically, it's the mu equals 3 class, and Ising is the mu equals 1 class. So the fusion looks very similar, and even the statistical space is very similar, except that this sigma field here has a spin 3/16. That's because it's a mu equals 3 class. So it's pretty much to get this double Ising-like topological order. But in reality, our A field is actually in SO4 gauge field. So we need to mod out the Z2 in this topological order. And mod out this Z2 means that we need to throw out all the lines that has total half spins and leaving only the integral spins. And formally, that's called gauge the one-form symmetry generated by this 1-1 line or Pacific bar line. And if you run the standard algorithm, you will find that gauging this one-form symmetry, you will get this torical topological orders, where the 1/2, 1/2 will split into 2 abelian anyons. That's the E and M. So we have concluded that our pure SO4 2, -2 transaminase theory indeed actually secretly describing the.
There's no funny percent of the 3 for 8.
No. Yes, there's no. Yeah, both of these two are when you gauge it, you get torical, and when in the torical, when you gauge the self-duality symmetry, you have the freedom to add Z2 as PT. That tells you which one. Okay. So we are using a very complicated transaminase theory to describe toricals, but the bias is that there's this transaminase theory has a Z2 flux conservation symmetry, and I show you that this will, in the low energy, exchange the E and M particle. So how does that happen? We use still the same trick. We will try to gauge this global symmetry. As I said, we first turn on this background terms, this I pi A cup W2 term. And when you gauge it, we will turn this background gauge field into a dynamic gauge field. And then we can integrate it out. And the equation of motion will tell us that W2 will be 0 now. So since W2 represents obstruction to lift SO4 to this double copy of SU2, when it's exactly equals to 0, we know that there's no obstruction to lift the gauge field into this 2 copy of SU2. So actually, this transaminase theory is basically SU2 times level 2 times SU2 level -2. This is what we get after we gauge the symmetry. So we know that before we gauge the symmetry, we have only the torical. And in the torical, there's only a single Z2 global symmetry that when you gauge it, you get this double copy of SU2. So we know that the symmetry we gauge is the Z2 self-duality symmetry. So this tells us that self-duality is realized as this flux conservation symmetry. Okay, that's complete our story in the positive mass side. We have topological order with self-duality symmetry. And now we run into the other side. The mass term is negative. We know that this phi field will condense. So it has an expectation value. And that means we will have a Higgs transition that this SO4 will be Higgs down to SO3. And in fact, this SO3 can be written as the SU2 over Z2. Particularly, this SU2 will come from the diagonal part of this left and right SU2. It's only this diagonal SU2 will keep this expectation value, this order parameter in balance. So our gauge field is now a diagonal SU2 over Z2. And since it's a diagonal, we know that the left gauge field and the right gauge field will be exactly the same now. And then the transience terms for this left and right one will just cancel. So we don't have any transience anymore. The theory is just a pure SO3 Yang-Mills theory with a global Z2 symmetry. So now I want to show you that this global symmetry in the SO3 Yang-Mills theory is actually spontaneously broken. And how to see that? We're still doing the same trick. We'll try to gauge the symmetry first. So if we gauge the symmetry, then this A field becomes dynamical. We can integrate out. We will find this second Stiefel-Whitney class, which now measures the SO3 obstruction will be vanishing. And then we can lift the SO3 to SU2. So in the end, the theory is actually pure SU2 Yang-Mills theory. And I suppose everyone will agree that we should expect that this SU2 Yang-Mills theory will confine to a unique vacuum. So we know that after we gauge the global symmetry, we have a trivial phase with a single vacuum. And by the standard arguments, when gauging a global symmetry, you know that means that before gauging, this global symmetry is spontaneously broken. And we will have two degenerate ground states. Okay, I think everyone agrees with me. So I have kept my promise that this phase diagram indeed naturally describe a phase transition between two phase gap spaces, one with Z2 torical topological order with this self-duality symmetry, and in another phase, it's a trivial phase, but the Z2 global symmetry is spontaneously broken.
Is there a way to see more directly that SO3 Yang-Mills theory mentions has two degenerate vacuum?
Oh, we don't know that. We do rely on this gauge.
But this is typically you gave two for degeneracy.
Yes.
This is in the trivial phase.
Well, it's a discrete symmetry, spontaneous broken. We just expect it should have two degenerate ground states.
Oh, I see. So that corresponds with the first order transition line curve.
Yes, yes. Yes, so at the neutral level, the phase are indeed match with the numerical results. So let's recap what we have done, and then we establish that this diagram works to describe the self-dual transition. So we start with this SO4 2, -2 transition theory. It describes these two topological order. If along one direction you gauge the global symmetry, you get the double SO2 transition theory. And if you gauge the Pacific bar line, you get back. And in particular, along this horizontal direction, we have this phi field, this real scalar under SO4, which means that it's a one half under the double S2. And indeed, that should correspond to this one half or sigma bar in the double S2. And the Higgs transition, then the phi field can have a Higgs transition to get the expectation value that spontaneously broken the Z2 symmetry because phi is charged under this global symmetry. And then along the top lines, you just also have the one half that are going to condense and drive a Higgs transition. And on the right-hand side, one phase has a SO3 Yang-Mills with a degenerate ground state, and the other one is SU2 Yang-Mills with a trivial ground state. And this whole map just fits. So this is one example that.
This is why I have a wide dimension because
yes, it does.
Space.
It does.
They have a four component.
The quantum dimension is 2.
Oh, I see.
Oh, you see from the top side. Because this one, this one half line has quantum dimension 2. And when you gauge this one form symmetry, you just throw out all the half integral lines. And the total integral line the same, remains the same quantum dimension. So this is an example that this Higgs tradition does align with anion condensation theory for this non-abelian anions, which is not always the case. It's just that here we find that the whole theory doesn't match with this anion condensation prediction. And that closes my story for the toric transition. But naturally, this field theory can. This theory can have a natural generalization. You just take this level k to be any integral, positive integral k, and they have two class. When the k is even and the k is odd, they have slightly different predictions. So when the k is even, you will find that this Z2 flux conservation symmetry always commutes some anions in the low energy. So it always does act as a self-duality symmetry. And the space diagram is very similar to the k equals 2 case. It's a transition where into a Z2 symmetry broken case with trivial topological orders. And when you have this theory, and now you can say some argument about the criticality, especially for a sufficiently large k, you know that the gauge fluctuation should be suppressed, and you expect that some critical component should approach this O4 Wilson-Fisher, and in particular, there's a maximum phi field, and you should approach the O4 Wilson-Fisher prediction, which is around 1.66. And you check the numerical results from, say, Adams group and the later results. And this numerical results fits around here. So it's even for the k equals 2 case, the numerical result is not that far from the large k prediction. So it's okay. Then you can check some interesting cases. For example, the next one is the k equals to 4 case. If you run this exactly same procedure, you will find that this SU to level 2 minus 2, when you condense the 2 lines here, you will get S3 topological order, ordinary discrete gauge theory. And this gauge theory is also well known that it has anion exchange symmetry that exchange two non-abelian anions. And in this case, C is a pure charge, F is a pure flux ions, so you could still call it an EM exchange symmetry. It still has a pi mutual statistics. And from this argument, you see that on the horizontal line, we're driving this one half to condense. And you try to match that with the anion content in the S3 quantum double. This one half will be a single non-abelian anions of quantum dimension 3, the C anions. It's a pure non-abelian fluxion. So the prediction is that if you only turn on the fluctuation of a single non-abelian fluxions, which is actually a singlet under this self-duality symmetry, you only turn on this fluctuation, you will actually run into a spontaneous problem of Z2 symmetry, but because the D anions, any condensable algebra that contains D will actually be a Lagrangian algebra, and there are two of them. There are probably many literature computed out, but this literature from Akia and Zheng has built up it explicitly. So you know that this cell, and you see that because one condensation is so A plus C plus D, the other is A plus Fn plus C, and these two are mapped into each other under this self-duality symmetry. So indeed, you will have some spontaneous brokenness of this self-duality symmetry, even though the field, the fluctuation, the D is actually a singlet under this self-duality method. And maybe for the odd case, you will find that in the end, your transcendence theory will still have this Z2 flux conservation symmetry, but nonetheless, in the ground state, it won't exchange any anions. So it's a very, it's almost decoupled from the anion contents. But you can, but it's still transition into the symmetry broken phase. And you can, for some simple cases, you can check it for example, in the K equals 1 case. This transcendence theory will describe a trivial TQFT with Z2 global symmetries. So this transition, if you make a guess, it should be our familiar 3D icing transition. So the conjecture is that this gauge theory will be IR due to the 3D icing theory. So we're saying that this, especially this icing thing, will be due to this SO4 monopoles. It's pretty much analogous to the U1 case, where there's a famous particle vortex duality. Here we find a Z2 cousin for it. And you can also run the K-3 case, then this will be a transition from this double Fibonacci to a trivial phase, where the Z2 will act trivially on the anions. And the transition is driven by the fluctuation of top also a non-abelian boson. That closes my talks, and I'll here for some future questions.
So there is a risk kind of start from image during a quality of the thing influence. After some values, the written off. The trait was discussed in detail in this SUN when at HQLT by Simon and in Morgan people like on the level. You try to explore what happens this square. You give it to the dual connection.
We will have a try.
Could be interesting.
Yes. Yes. But in that case, it's not good. It's like as well level K due to as you K level 1, it's not true engagement of global space, I suppose.
No, that's level 1.
Yeah.
The case are more than one. What slash suggestion.
Yeah.
I think they got it. Oh, that's very good.
Related to the recent work by Yunqin and
It's not the
yeah.
So,
It's a
which one?
what the relationship with Ryan is.
Oh, it tries to address the similar questions, but I think they use a billion gauge series, and that does have some problem. There's also some existing literature about trying to use a billion gauge series, but they all have some problems. Particularly, the closest one is with this 2 U1 gauge theory and with some neutral transcendence terms. And that one works very nice for Zn transitions when n is greater than 4. So it works. It works like for example Z4 toroidal Z4 topologies with self-random symmetry, but there's no analogous control, analytical control when you're approaching K equals 2. And for the very small range that you do have the control, that actually doesn't predict doesn't predict this SSB phase. So it cannot predict Z2 SSB. So this Z2 part is still also. This is probably the only one that's this.
I guess the paper by Ryan and Thomas actually is studying a slightly different system.
Yes.
Where there's the U1's tree. And instead of transitioning to the trivial phase, it transitions to a spontaneous breaking result phase.
I think they also see when approach K, little K equal 2, it doesn't.
it's good. So
It has no analytical control when approaching K equals 2. We cannot say that.
No questions. Okay, let's think. Right, this is the observation and the particle.
Very simple.
It's not just well, like, I mean, it's motivated by something, but it's like, but, I guess in order to make progress, they, take it forward. If they say, here, type for you guys. That's it. How much we're able to take. I think they, I would say that they're gonna be, yeah, but they don't want to think about what else.
Oh, they have some options.
Yeah.
You add those, rating, what happened? Anyway, there's no.
Right, that, yeah, I think that, but I think they should say it, so, we're in now, this problem.
You want, yes, that,
Oh, yes.
Okay, and this is your microphone. So, and you have to unmute it when you start from. Unmute it, someone else. So, I think that we can just. That should work. Just check that. You can point. And you should have.
That's the point.
So. Yeah, exactly.
Okay, let's get started. Our next speaker is Zheng. Take it away.
Thanks. I want to first thank the organizer for putting together this meeting workshop conference. And today I would like to share with you our recent lab progress in understanding the penetrating preferential theory and its application to multiple set bounding problem. Okay, so this talk is based on this paper that we put out last month with my excellent student, Wenjie. And he's actually an undergrad student and he's looking for grad student. Okay, so, and also our work is also heavily inspired by these two papers, especially the first one. Okay, equally the second one. And also there are a lot of recent progress, like the work, for example, talked by Andrea yesterday, and also talked by Lucas on Monday. So, all right, so what's this talk about? So the talk is about the free premium, the wild premium, the 1 plus 1t. So we just take n copy of compact wild premium 1 plus 1. And this is the Lagrange. This model is very simple. There are many sense in which it's simple. First of all, it's a free field theory. So there's no place to hide. We should understand everything about it. And second, it's a chiral. So it's a building block for the non-chiral inductor. So it's, in this sense, it's much simpler. And also, yeah, so like it's built up from the simplest Brownian parallel conformal field, which is C to one half on one. So yeah, so it's very simple. And it's also very interesting because it appears in many contexts in physics. For example, in condensed matter physics, it appears as the edge state of the quantum integer on the top, and also in string states. All right, so the main question I'm going to ask is, what are the global symmetries? The most naive ones are if you have a UN symmetry that rotates fermions, and also a charge conjugation symmetry, and which maps the side to side. Surprisingly, even though this theory is very simple, so far I think understanding the full set of symmetry is still an open question. And the main claim today is that this theory enjoys a lot more non-invertible symmetries. So how do we find these exotic interesting symmetries in the simple model? Well, the trick is the unfolding. So you start with another system, which is the n copy of the Dirac fermion with a boundary condition. Suppose you find such a boundary condition, and you float it to the heart, so the boundary condition preserves half of the conformance. So the boundary condition is also represented by a boundary state. So it's given is determined by this Ishikawa condition.
If you could add.
Okay, it's fine. So the start with the Dirac fermion, and with a conformal boundary condition, and you just unfold it. So just fold the right mover to the left. So you have basically for Dirac fermion, and you have to post the left mover and right mover. Left mover is incoming mode, and right mover is outgoing. So you have a boundary, and you just unfold it, and the left mover you keep the same. Sorry, going mode, and the outgoing mode, you just flip the direction to the right hand side of the plane, and after unfolding, the theory is just an n copy of the wild fermion. And what does the boundary condition become? And becomes some conformal boundary condition. Well, first of all, the Dirac fermion has a conformal boundary condition. So after unfolding, you are generally expect to get a conformal effect of the wild fermions. But for the chiral theory, conformal effect is also a and which means that the boundary condition becomes a topological. And today, so we usually use a defect in topological as a symmetry of the system. So it means that D is a symmetry of the unwild fermions. So the slogan here is that the conformal boundary condition should be regarded as a source for the globals. And this happens in very particular case in the Dirac fermion. You apply this slogan to other systems, you may know. But for Dirac, for the free fermions, this slogan. So we want to find the symmetry of the wild fermion. So and the slogan tells that we should look for the boundary condition for the Dirac fermion. So what's that boundary condition? And the most easy ones are the boundary conditions, which are like you impose on linear conditions between the different. These are usually called the linear boundary conditions. And after unfolding, what symmetries are observed? So so for this boundary condition preserves, say the left one preserves the UN symmetry, and the right one preserves the UN times the top condition. So after unfolding, and so these boundary conditions, you can easily calculate that they give rise to these events. charge complications. And the conformal, the set of conformal boundary conditions are not just these, but there are many more conformal boundaries. And we should ask, if we do the unfolding for those boundaries, what do we get? And to find those more exotic conformal boundary conditions, there are fermions. Turns out that the symmetry will play a very important role. So what do I mean by that? So we should start with a Lord. So this is all because of a Lord. The Lord says that whenever you have a symmetry that is allowed free, you should be able to find a conformal boundary condition for surfaces. So so how to understand this form? So when the system has a non free constant G, you can try to turn on some gap interaction of the system while preserving G, so that the system can be trivially gapped out. So it can be gapped out into a trivial neutrality. And so the conjecture, the statement here is that whenever G is not free, you can always do this. And it has been first initially proposed by Cyber string conference and later proved, I think, in a talk actually by Philip Collins. And there were many more examples. For example, the earliest ones, I guess, was given by Xiaogang and Zheng, and so far this forms a community called symmetric mass. Now, once if you admit that there is also always a gapping potential, then you can just turn the gapping potential half. So once you do this, then you can form an interface between the original theory and the trivial. And this interface, because the gapping potential preserves the G symmetry, so the boundary condition, the interface between the trivial phase and the original system should also preserve the G symmetry. And the law says that whenever you can do this, you can always find a simple boundary that is indecomposable for the sum of different boundary conditions. And yeah, so the law is about the simpleness. Yeah. So this half gapping tree does not guarantee that the boundary condition get as simple. But in many examples, people check that this trick always works and you get a simple boundary condition. And indeed, there are several counterexamples that validate this law. And I actually gave a talk 2 weeks ago in GTI. And so yeah, if you are interested.
But for your purposes, do you really care that it's simple? You can still get a symmetry over it.
That's right, but you'll get a direct sum. Okay. So yeah, so then if you apply this half gapping trick, then you will get a boundary condition preserving. So let's apply this trick to the free framework. So actually, it's so first of all, in the free framework, okay. So for the free framework, I already said that there is a UN times the charge communication symmetry. And if you look for scan through all the subgroups of it, you can find the anomaly, you can classify the anomaly symmetries. And not all of them act in the same way on the left mover and the right mover. There are many examples where the symmetries can act on the left mover and the right mover in the direct framework in a different way. They carry different charge. So after unfolding, the fermion on the left of the defect on the right of the defect will carry different charge, different representation of G. So it means that so if you assume the law is correct, then it means that there is a conformal boundary condition preserving this characteristic and the chiral symmetry should be above. And in the case when G is a special U1 subgroup of the UN charge transition, for instance, when G is a U1 to the nth power, then this boundary condition has been explicitly worked out in a paper by in a series of papers by Philip Smith and David Tom many years ago. And in general, when G is not non-abelian, finding such a boundary condition is quite difficult enough. And so far, for some G, people still don't know how to explicitly construct the whole boundary, those preserving those things. But for purpose of this talk, we're going to assume that this such boundary condition always exists. So we have discussed the boundary condition that preserves some exotic symmetry, like chiral but anomaly free symmetry. So let's call them the symmetry preserving boundary condition. And if you unfold, the boundary condition becomes a topological defect, and topological defect should satisfy this particular relation with the global symmetry that we want to preserve on the boundary. And it means that when you suppose you have a topological defect on the left side of the wall of the defect. So this is D and this is G. If you push this UG to the left side of the wall, it becomes the VG. So this relation is called intertwining. So the D intertwines the G thing, or more precisely the G representation. Okay, so a quick summary of what has been discussed so far is that suppose you start from an anomaly free subgroup of the vanilla naive UN times charge conjugation invertible symmetry of the Dirac fermion. Copy of that, and pick an anomaly free subgroup, and you should find a boundary condition preserving this G symmetry. And if you unfold it, the corresponding topological defect would intertwine corresponding G representation. So in the rest of the talk, I'm not going to use the fact that this D is explicitly constructed. I'm just going to assume that D satisfies this intertwining. And from that, I'm going to construct the D explicit. All right, so before moving on to concrete examples, let me mention that this way of thinking has a strong intimate interplay with the fermion boundary scattering or fermion monopole scattering that Andrea talked about. So, in the fermion boundary scattering problem, it says that a boundary condition preserving some non-anomalous but chiral global symmetry often gives rise to what's so-called a categorical scattering that defines. So it means, more concretely, it means that if you scatter a fermion onto the boundary, then the outgoing state is generally not a local, not an operator in the untwisted sector. It's an operator attached to a line which is intertwisted. And after unfolding, this boundary condition becomes a topological line. And this topological line can act on the fermion. And once they act on the fermion, so it can act on this fermion. So once this topological line acts on fermion, and the result is that you will get some twisted sectors. So this is the hallmark of the non-invertibles. So usually the non-invertible symmetry does not map local operator to local operator, but it will map local operator to some twisted set. And you can interpret the categorical scattering as a result, as a consequence of this non-invertible symmetry that you get after unfold. Right. And also, yeah, so intuitively, we can either like deal with the problem of the boundary condition or deal with the problem of finding some topological defect. And the latter is intuitively more is easier because it's purely kinematic. It's just a problem of the symmetry. Yeah, maybe solving the latter problem is a bit easier. And this way of so suppose you find a topological defect in the chiral you can just pull back and you get some hyperboreal success. And this way of thinking about the fermion boundary problem opens up the possibility of solving the fermion boundary scattering problem, and some of which are still open. In particular, when the symmetry you want to preserve is not obvious.
那个有分数对题呢，一般是 selection。
Yeah. And okay, so in the rest of the talk, I'm going to focus on two examples. One is for the abelian tree, and the other is for the non-abelian tree. So first, the abelian tree. So the G is the U1 to S power. This N is also the number of the fermions. So you have so let's start with the setup of the direct fermion. So you have the left mover and the right mover. They carry some charge. So you have a n number of U1 symmetry. They are labeled by this index A. And the charge of the left fermion, the ith component, carries the charge QAi. And the right mover carries charge Q tilde I. And they act on the fermion in this standard way. So lambda is the like U1 parameter. It's defined modulo 1. Now, then you want to demand that the boundary condition preserves this U1, and this U1 to this power is anomaly free. So anomaly free condition means that the charge is satisfied with quadratic, because the anomalies are quadratic, depends quadratic charge. And it turns out that it's simpler if we introduce another symbol, which is called R matrix, which relates the Q and Q tilde in this way. And anomaly free condition implies that this R matrix is orthogonal. And I want to highlight that this R matrix is in general not an integer value matrix, although Q and Q tilde are in general they contain fractional matrices. In the simplest example, for instance, Lucas discussing on Monday, so in the 3, 4, 5 zero model, the R matrix is 4, 4, 3. So you see every element is actually fractional. And after unfolding, so then we want to demand that this topological defect we get satisfies this intertwining. Okay, so we want to ask what kind of defect satisfies this intertwining. Well, first of all, I want to prove that D must be non-invertible. It cannot be uninvertible. It cannot be uninvertible. Why? Suppose D is an invertible defect. I can consider D inverse or D conjugate. Whereas, okay, so D permission conjugate, which is equal to D inverse, I can just move it to the other side. And so UA is D inverse, D conjugate, D. And suppose B is an identity element, acting on the fermion. Implies this relation implies that U must be identity. So concretely, you substitute this formula into definition of the charges, then you find that B equals to 1 implies that this vector, nth component vector must be integer valued because like the thing on the exponent must be integer times 2 times. And similarly, u equals to 1 implies that this on the T must be integer. And if you recall our definition of R matrix, R matrix relates the Q and the QQ. So R matrix will generally map, if it's invertible, D is invertible, then our corresponding R matrix would generally map an integer vector to an integer vector. However, as I emphasized before, R matrix in general contains fractional. So in general, it's not possible to map an arbitrary integer vector to an integer vector. when it's possible? It's possible when the R matrix is the integer vector as well. And in this case, the corresponding D will be some like swapping, some operations which just exchanges the terms. But in general, like when R is a contains the fractional coefficient, then of course, what I showed here is that this D must be null. So I proved that the D must be null when the D satisfies this intertwined equation and the corresponding R matrix that contains the fractional. Okay, so for general R, what is D? So D is non-invertible, but what is D? And the simplest non-invertible defect that we are familiar with are the duality defects associated with gauging some finite digits. So let's just assume this and see if we succeed in identifying this D as a duality. So in our paper, we presented a more convoluted discussion to find this D. But Andrea told me that there is a symmetry divide, so I want to explain this proof. And this proof is actually used in his paper in the context of a 3-4-5 period example. And the point is that this proof actually works in general. So what's the idea? The idea is that so you have this intertwining. So if you assume that the wrong side, for instance, the D is identity, then you can try to find what are the corresponding U's. So if you can find such a U, so it means that the U is absorbed by the D defect, And this is precisely what the duality defect is doing. So a duality defect can absorb whatever symmetry operator that is that it engages. And if you apply this solve concretely, then you're going to identify that the symmetry that you want to the D is gauging is actually this gamma. So I'm not going to walk through the details, but after some simplification, you are going to find that this gamma is actually determined solely by this matrix R. So this and in this expression. Okay. So you can actually to simplify this expression a bit more and to find explicitly what symmetry, like what subgroup, what finite appearing symmetry you gauge, and what the charge the fermion carries under this gamma. And there is a very concrete algorithm to extract all of these data. And the key idea is to use the Smith-Norman form. But anyway, so you can explicitly find for instance, the order of the symmetry U and the charge of the fermion carries on Z and U. So everything is very concrete, so it's a straightforward operation.
Sorry, so are you saying that these intertwining defects are always duality defects for this group gamma?
Yeah, in the case when G is the U1 to the nth power.
Ah,
with this, yeah. in general, it's no. Yeah. All right. And actually, you can directly prove that the fermion is still due under gauging the gamma field. And you can explicitly see it at the level of the torus function. And in particular, this torus function shows us that if you gauge this gamma, there's no discrete torsion. You just directly gauge, and you find that the function will come back. Okay, so far is the first example, a bit inches. How many minutes do I have? Okay. So the second example, which is the last example I want to talk about, is Wenjie is SU2. And it's an SU2 which is not an arbitrary model, but it's a model, famous model called 15789 model. So what is this model? It's just a free fermion. So you again start with the direct fermion. So you have the ingoing mode and the left mover and the right mover. And in total, there are 15 number of direct fermion. So the left mover carries so the theory has an SU2 symmetry, and the left mover carries the SU2 representation. So one fermion carries transform trivially on the SU2, and the 5 fermions transform on the dimension 5 representation of SU2, and the 9 fermions transform on the dimension 9 representation of SU2. And similarly for the right moving fermions, they transform on the 7-dimensional representation of 8 dimensions. So it's also like a free fermion with some anomaly-free SU2s. Actually, so this SU2. So first of all, we have to check that this SU2 is anomaly-free. So the SU2 paraanomaly is classified by an integer. So let's call it A. And so it's a result, but so the anomaly is well known as the anomaly of the well fermion. Transforming of the SU2 in the nth dimensional representation is given by this complicated formula. So n times n squared minus 1 over 6, and it's an integer. And in particular, when n is 1, then it's a non-dimensions, but in general, n does not. And you can check that the anomaly of the left moving fermion and the right moving fermion explicitly cancel each other in the case of direct fermion, which means that the anomaly after unfolding the anomaly of the fermion on the right plane and the anomaly for fermion on the left plane are matched against each other. So it makes sense to have a topological defect. Okay. And if you assume the law that I mentioned in the beginning, there must be a boundary condition preserving this SU2 symmetry, although the explicit construction of this boundary still is, which also means that the defect, topological defect after unfolding is also missing. Okay, so I'm not going to find such a defect. I don't know so far. But I want to show, okay, so first of all, I want to show that this defect also must be non-uniform. So how to show that? You can just consider the Cartan subgroup of SU2, and here I list the charge of the Cartan subgroup. Then maybe naively we can just apply the algorithm that we discussed previously and apply to this case. So we just find an R matrix that relates with Q and Q tilde. But here, Q and Q tilde are not n by n matrix, it's just n by 1 matrix. So it means that this R matrix is not uniquely determined. It's highly undetermined, but you can still find many candidates that satisfy this condition. And but the one particular property of R matrix is that it cannot be all integers. Why? Because the Q's are all integers, And R times Q is Q tilde, but Q tilde has a nothing. So it means that the R matrix cannot be all integer vector. So it means that according to the result that we proved before, this D must be non-invertible. If it's invertible, then the R matrix must be integer vector. Okay, so it's non-invertible symmetry. But what is it? There needs to be some duality but associated with getting some invertible abelian group. And I want to show that it is not. So how do we show? Okay, so first of all, this relation, as I mentioned before, that it does not uniquely determine the R. And if you apply the previous operation, and maybe you can just like here, R is not uniquely determined. So, but maybe you can just pick one solution of R satisfying the top equation, and you just apply the algorithm that I sketched before, and you just explain that so the fermion is invariant on gauging this equal. This finite. But the problem is that this gamma, so this duality effect associated with gauging this gamma does not intertwine with SU2 charge square. So it means that whatever gamma we choose, it cannot be desired topological defect that intertwines SU2 charge.
Sorry, the duality for gauging gamma is a symmetry of the theory.
It's a symmetry, but the only problem is that it does not preserve, does not intertwine SU2.
But it's not necessarily one or
Yes, that's right. Or in other words, after folding, the corresponding boundary condition does not preserve the SU2. It generally transforms. Under SU2, you will become the other boundary. Okay. Yeah, that's right. Yeah. So it's not good. So how many? 5 minutes? Yeah, so here's the okay. So more concretely, so why the SU, so this D does not intertwine the SU2 symmetry. Intertwining the SU2 symmetry means that there, like, if you have a D of like topological defect, and the U symmetry operator and the V symmetry operator can meet topologically at the junction. And if you have this D and D dagger and put them close to each other, they can fuse into an algebra object, A. So A is generally a sum of discrete elements. So it means that this UG, which is a SU2 element, commutes with this non-simple object A. But because UG is a SU2 and SU2 is a simply connected Lie group, it cannot map one discrete symmetry element to another. So it means that U commuting with A means that U commuting with arbitrary elements. And this stronger condition can be shown to be non-compatible with any choice of gamma. So any choice of H, which is any two variables. And I have a proof I have 2 slides of proof, but then maybe I'll skip it. But the consequence of this statement is that the fermion boundary scattering, the outgoing state, which should be attached to an element in A, cannot be uninvertible. It must be a non-invertible. So here is the proof. So basically, the idea of the proof is as follows. So so because the gamma should commute with SU, And in particular, so it means that the gamma should be an identity element in each multiplex of SMT. So it means that for the left mover, these 5 elements should be of the same value in gamma. So this is which are the charges of the fermion of the gamma. And the latter 9 elements should also be invariant, should also be identical, because they have to change. The gamma should act as identity that fixed as 0 to multiplex. So once you have this relation, then then you can split it plug in into the formula, the definition of R. So this formula I'm going to show you how to derive it, but it's just a chart me. That R matrix depends on the choice of Q and N. And previously we used R matrix to derive Q and N, but here I just write down the formula explicitly. And this means that the fractional part of R is completely determined by Q and N. And because Q and N satisfy this particular relation, means that the fractional part of R should also satisfy. So here I just decompose R into the integer part and the fractional part, and the fractional part also satisfy this. And once you have this, it's just a few lines of derivation. So Q by definition is R times Q. And if you take the model 1 value, it becomes the C times Q, because the C is the fractional part of R. And you just like expand this expression, and you find that the expression must be 0. So it means that Q is therefore is an integer, which conflicts with our starting point that Q must contains the half. So this is just an ideal proof. All right. So I proved that. So I proved that so I proved that the corresponding the topological D is not a duality, but associated with space in a finite abelian. But in addition, it means that this D, if you fuse with D dagger, it gives you the algebra object, which is the sum of the non-zero. And in particular, in the scattering process, the outgoing fermion, outgoing particle should be tapped to some non-invertible ones.
There's some of feedback to reach an algebra.
Yeah, it must be an algebra, but which algebra it is, we will talk about. All right, so this is a summary, and I just want to highlight a question in the end that for general G, how to determine like this topological defect is still an open question, and it should be interesting. Thank you.
So this is beyond family.
So the abelian case is within Hamilton family, but this non-abelian case is beyond Hamilton.
Like people simply like that.
Yeah. So yeah, it depends on what you mean by singleton. If you mean singleton for including the G symmetry, then it will become very complicated.
So and base field.
I think it's what we very complicated.
Yes.
So is it fair to say that these Mario-Amagami defects give you a class if you want to get intertwining defects in all of them?
Right.
Second question is, do you know what the smallest number of Majorana fermions is that it's a non-invertible finite quantum dimension?
At least two complex algebra. has
Right.
have none.
Just three, you know, three, that's,
Well, two of them have, but three should also have.
sorry, I meant, yeah, three Myron.
Oh, three more.
Okay.
Yeah, haven't thought about it.
And then the last question is, so ostensibly in fermionic theories, topological line defects are described by superfusion categories, so
That's right.
there's also these, I forget if it's M or Q type lines that have the Myron law.
Yeah.
I think all yours don't have that feature, so have you thought about how to get these lines?
I
This
think
other flavor and what the interpretation?
Yeah. So I think we better have, okay. We better have a non-equatable line with point dimension square root of 2 in that case, right? And I think if you scan through the spectrum of this duality defect, some of them indeed have such structures. Not still sure, whether they are indeed a Q type.
Yeah, I think just having one of the square is
It's not enough, yeah.
I have a question, so, I guess when you talk about this argument in the context of the symmetry SU2, but I guess maybe generalized to any degree.
You can ask the same question for any, and most of them people don't know.
But did your argument really depend on the statement of the institute?
No, I think this the argument can be more general.
I mean,
But the idea can be generalized definitely, but the statement,
it's just the conclusion that it's kind of.
yes, in the case of the SU10, I guess so in this SU2 case, particular feature is that if you focus on the charge of the U1 Coulomb subgroup, some of them are like, so for the left mover, it's all integers, for the right mover, it's fractional. And in this case, they can be like 1/2 plus. So in the case of SUN, I guess the statement is that if you have an assignment of charge such that the left mover are all integer, but the right mover are 1 over n times plus. Yeah, that's it. That's it.
I guess I have one more question, which is, so you said the symmetries of the direct fermion lead to topological defects.
The boundary conditions. Boundary.
Well, you said that symmetries give boundary conditions.
That's right. So basically, I'm trying to use a known particle to sort of bootstrap the new symmetry using the boundary.
Yeah. So the question I want to ask, in the next one, we're going to get the very large symmetries of the lattice regularization of direct fermion. Do you think that symmetry is specific to defects?
I don't know.
Okay. All right, no more questions.
Well, we haven't Okay. Yeah, I guess you can generalize it.
We can do it. It leads to.
I see.
Interesting.
I see.
Yeah, I don't want to give the clarification on the boundary. We have been on solve.
Nowadays. So it's so big, it's all nowadays.
All right. Okay, so yeah, thank you for the invitation. Thank you all for making it out here on another hot day. Yeah, I'm excited to tell you about some work with Xue Chao and one of Xu Heng's graduate students, Elijah Lustig, both of whom are at MIT. And something that everyone in this room is very familiar with is that there are two main frameworks to describe a quantum system. On one hand, there's quantum lattice systems, which for this talk, if I say lattice, I always mean a spatial lattice, just time. And on the other hand, there are quantum field theories. And we should be very thankful for these two frameworks. Without them, most of us probably wouldn't have a job. And if we didn't have a job, we probably have to get a real job. And real jobs don't necessarily send you to Paris. So they've been successful in all different types of physics, from condensed matter to high energy, to quantum information, and also pure mathematics. And they're different frameworks, but they're infinitely related. Namely, there's this idea that I can have some quantum lattice model, and I take the so-called IR limit, or I do some R machine. And I should land on some quantum field theory that describes aspects of quantum lattice. And something I've been very interested in is the following idea. Formalizing. So I want to imagine having some notion of I want to imagine having some notion of some abstract space of all quantum lattice models. And there's some machine that maps that or has some relation of that to the abstract space of all quantum field theories. And I'm not going to make this precise. I don't think it is precise at all right now. But I think this is like a guiding philosophy, and I think it's important to try to make it more precise. But it's obviously very hard to make this more precise, right? Like, what do you mean by the space of all quantum lattice models, the space of all quantum field theories? How liberal should we be with what we call a quantum field theory to accommodate certain quantum lattice models that have things like fractons? But I think there's a first starting point, which is to start by working at the level of the kinematics. And instead of asking the ambitious question from the last slide, we can instead ask, well, I have some notion of the space of all quantum lattice model symmetries and anomalies. And there's some relation to that, invoked by this infrared limit, to the space of all quantum field theory symmetries. This is a bit more of a manageable question. And in this arena, you can ask many questions, and these are three questions people have already asked about. So the first you can ask, well, what is the space of all symmetries for quantum lattice models and functions? Another question you can ask is, if I fix my quantum lattice model symmetry and look at all the different theories that have that symmetry, what can that symmetry become in the ion? And the third question you can ask is, which quantum field theory symmetries can arise from some quantum lattice model? Namely, I fix some quantum field theory symmetry. Is there some quantum lattice model symmetry that can arise? And in this talk, we're going to be focusing on invertible zero form theories. And we're going to be thinking about a question that's most similar to the third question on this list. Namely, we're going to be thinking about which quantum field theory anomalies of invertible zero form symmetries can arise from quantum lattice model anomalies. And we're going to look at a specific class of quantum lattice models. Namely, we're going to look at quantum lattice models that have so-called tensor product Hilbert space. Maybe it's a graded tensor product of those fermions. And the local Hilbert spaces should all be finite. Okay. So that's the arena that we're going to be playing today. And the theory of anomalies for ordinary symmetries in QFT is very mature by now. And there's very sophisticated frameworks to understand the different possible anomalies. But in quantum lattice models, the theory of anomalies is kind of some sense in its infancy. And it's a very active direction right now. So because we're going to be talking about anomalies in lattice models and what they become in quantum field theories, I want to remind you of some basic things about taking a UV to IR limit when you're talking about. So suppose I have some UV symmetry and it's described by the group GUV. And suppose there's some anomaly omega UV. And if you want this anomaly to just be some group cohomology, you know. So if I start with this UV system and I take the IR limit, it's going to induce some homomorphism that relates the UV symmetry group to the IR symmetry. And this homomorphism implies a relation between the anomalies of the UV and the anomalies of the IR. Namely, the homomorphism induces another homomorphism, which tells you how the anomaly in the IR relates to the anomaly in the UV. Okay? And given this pullback homomorphism, rho star, you can state what anomaly matching is, which is a requirement for the IR limit to be consistent. What anomaly matching says is that if I take my IR anomaly and pull it back to the UV anomaly, that better be the same thing as. Okay. And there's two things I think everyone are familiar with in this room that come from this. So the first is that if I have some non-trivial UV anomaly, it has to imply that there's some non-trivial IR anomaly. This is what we usually say, anomalies are chain variants. So really, if omega UV is non-zero, then omega IR must also be non-zero. The other context that people are familiar with is when the UV and the IR symmetry groups are the exact same. And what this tells you is that if the UV and IR symmetry groups are the exact same, then their anomalies have to be the exact same. I think most people, when they hear anomaly matching, this is what they think. They think, oh, anomaly matching means that UV and IR anomalies have to be the same. But this is not true. Like, there's a more general notion of anomaly matching that accommodates this very common situation where the UV and the IR symmetries are different. Okay, good. So one more piece of background I want to talk about with anomalies for invertible zero-form symmetries is this notion of an anomaly's order. And the order of anomaly is the following. So it's the smallest integer, n, such that n times omega in this additive notation of the abelian group of anomalies is 0. And what that physically means is that if I take some anomalous symmetry, some theory with an anomalous symmetry, and I take the n copy system of it. So I take n copies and stack them all on itself. Then the diagonal G symmetry of that n copy system will be anomalous. And it corresponds to, in one higher dimension, the inflow theory having order n under stack. And an anomaly can have order 1. And if an anomaly has order 1, then that's what we mean by when we say that an anomaly, that's what we mean when we say that a symmetry is anomaly free. So that's really, one more terminology. Okay. So if order omega exists, then we'll say that omega is a finite order anomaly. And if it doesn't exist, then we'll say omega is an infinite order anomaly. And oftentimes when omega is an infinite order anomaly, we'll say that order omega is infinite. Something that's really nice to prove is the following. So the anomaly matching condition on the last slide related the IR anomaly with the UV anomaly by the pullback. The anomaly's orders do not need to be the same under that pullback to be satisfied. And what you can prove is that there's an inequality between the order of the UV and the order of the IR. When you go from the UV to the IR, the order of the anomaly is either going to stay the same or increase, but can never decrease.
Can we explain why?
Yeah, sure. There better be results. That's okay. No. Yes. Wow. I wish it'd be more like that audience. Okay, it's super simple. This is the anomaly matching condition. Let me raise both sides to the order of the it's so simple I can't remember it all. Yeah, I think you raised the order of the IR anomaly. Here I'm assuming that it's finite order. This is equal to 1, and that tells you that the order of the IR anomaly has to divide the order of the UV anomaly. Or sorry, the order of the UV anomaly has to divide the order of the IR anomaly. And then that implies that condition. No, not that I know of. Yeah, I'm very tempted to call it an RG monotone, but usually with an RG monotone, it's like each point of the RG flow, you have something. This is really like for like the deep UV and the deep ion. Right, so it's really like extreme point. Okay, very good. So I want to do a very simple example. Like those two slides, if you know it, that's very familiar stuff. If you don't know it, there's a lot of new things I went through really fast. So simple example of quantum mechanics. And I can consider a quantum mechanical system that just has 2 qubits. Okay, and they'll have Pauli operators x1, z1, and x2. And I want to consider the following Hamiltonian. And this Hamiltonian has a D8 symmetry generated by these 3 operators. So CZ, this is the controlled Z gate. The controlled Z gate, it equals 1 if both qubits are notched down, it equals -1. And the other symmetry operators will be x1 and x2. And it's very obvious that the symmetry operators B and T can be with Hamiltonian, and it's pretty quick to see that the symmetry operator A also can be. And they generated D8 symmetry because they satisfy these D8 relations, where this is the basis for D8 is an extension of Z2 times Z2 by Z. Good. So the IR of this Hamiltonian, well, in quantum mechanics, when we say IR, we really just mean the ground state space. The IR of this Hamiltonian, it's the Z2 equals -1 eigenstates, right? You can quickly look at this Hamiltonian. There are 4 eigenstates. There's 2 ground states that have Z2 equals -1. And there's 1 excited state, I think that has energy 4. And then another excited state that has energy 8. Okay. And if you project into the ground state space, you project to Z2 equals -1 or C equals -1. The D8 symmetry operators become this. So the D8 symmetry operators in the UV and the IR, they become Z2 times Z2 operators, and they form a projective representation, so they have a non-trivial anomaly. So in terms of this row language, the image of rho is Z2 times Z2, but there's a non-trivial kernel, right? The Z2 generated by C goes away under the RG. And this is a very simple example of what's called an emergent anomaly. Because in the UV, there is no anomaly. In fact, it's really easy to see there's no anomaly because this Hamiltonian, multiplied by a minus sign, then there's a unique ground state. So there's the one-dimensional representation. But in the IR, there is some anomaly. And if you go through the pullback rho star for this quotient homomorphism, you'll see correctly that the IR anomaly is trivialized when you pull it back. Something else that this highlights, which is nice, is this anomaly inequality, the order anomaly inequality I showed earlier. In the UV, there's no anomaly. Okay, it's anomaly free, so that means its order is 1. And the IR, the order is 2. So it satisfies the inequality. Okay, so that was kind of the warm up to get everyone onto the same page. And now I know it's hot, so I'm going to give you a TLDR, which stands for too lazy didn't read. It's a summary. This is Zoomer speak for summary, okay? Okay, so here's a TLDR. So we just talked about the order of an anomaly. And infinite order anomalies are very elusive in quantum lattice models. And in fact, there are no-go theorems proven that say that there's more assumptions in this, but say that if you have a compact locality preserving symmetry in the types of quantum lattice model systems I'm considering, all anomalies have finite order. Okay. However, as we all know in quantum field theory, infinite order anomalies are the more ubiquitous ones. If you go to someone on the street and ask them, the first anomaly they know of, okay, they'll probably be very afraid and run away. But if they happen to be a physicist, they'll probably give you some perturbative anomaly with Feynman diagrams, right? And that's an infinite order anomaly. And not only are they more familiar in QFT land, but they're really cool because they imply Gauss, right? So they're very strong anomalies.
Question.
Yeah.
No-go theorem is finite on-site space, or?
Yeah, that's right. So they're for the types of quantum lattice models I'm considering here. There are examples of quantum lattice models with infinite order anomalies if the local Hilbert space is infinite dimensional, and there's some like Gauss law constraint too, in the lane type models. Okay, good. And the punchline for this talk is the following. So we're going to consider 1 plus 1D fermionic quantum lattice models. And we'll argue the following. We'll argue that if you take something called an Onsager symmetry, which we'll get to encounter in a moment, and you add a lattice CPT symmetry, that will produce an anomalous symmetry that has infinite order. Okay. And this Onsager symmetry, as we'll see, it's a lattice realization of the chiral anomaly in a massless drop. So it's a lattice realization of the axial of the vector U1 symmetry of a drop. And the symmetry group is very complicated. It's non-compact. It's infinite dimensional Lie group symmetry. So it seems to obey this no-go theorem in 2 ways. Firstly, the Onsager symmetry is non-compact. Okay, so that part goes away, the compactness. And also we have a CPT, so it's going to involve some reflection. And reflections aren't locality preserving. So it's going to also get around this other part. Okay, very good. Yes?
The Onsager symmetry suggests that the system is integrable.
There's some sense that that's true. I think it depends how you define integrable. So there'll be an infinite number of operators that commute with Hamilton. Yeah, but that's true for any infinite dimensional Lie group. There's infinite number of generators. So good. Any other questions? So really the rest of the talk is dedicated to just explaining this bottom half of the slide. And things are now going to get very explicit and very simple, hopefully very simple. And so we're going to consider, this is our setup. So we're going to always be working with some finite lattice. We'll always be on a ring, okay? So the so-called periodic boundary condition. And we'll always assume the number of sites, just for simplicity. Nothing goes wrong if you have the sites being odd, just add some extra space to it. And on each site, we're going to place a single complex fermion. And the complex fermion will satisfy the canonical anti-commutation relations. So as a starting point to ground ourselves, I want to start off with this staggered fermion Hamiltonian, written down before I was simple tight binding quadratic fermion Hamiltonian. And this is a nice starting point because in the IR, this Hamiltonian becomes a free massless Dirac. And if you haven't seen it before, it's very easy to see. You just go to momentum space, it diagonalizes the Hamiltonian. And there's a single particle dispersion that looks like a sine. And you have a left moving fermion appearing at k equals 0 and a right moving chiral fermion appearing at k equals 5. Good. So the symmetries of this 1 plus 1D massless Dirac fermion QFT, they include these vector and axial symmetries. The vector symmetries will rotate the left and right moving chiral fermions by the same phase, while the axial will rotate them by opposite phases. And there's a natural question, which does this IR symmetry arise from some UV symmetry of the Hamiltonian? Is there some UV symmetry that when you go to the IR, that UV symmetry becomes these U1 axial and U1 vector symmetries? And the answer to that is yes. And this is something I figured out with Arco Chatterjee and Chang Shao maybe almost 2 years ago. And you can check it explicitly. I'm not going to show you the derivation. I'll just show you the result. And the result is the following. So it's convenient to write the complex fermion C in terms of these real Majorana fermion, A and B. Okay? And in terms of A and B, we can write down these charge operators. And you can check these charge operators, commute with that staggered fermion Hamiltonian, and they also have integer quantized eigenvalue. So they both respectively generate a Yunqin symmetry on the lattice. And furthermore, I mean, the model is exactly solvable, and you can see what these charge operators become when you go to the IR. And Q0 in the IR will become the vector charge of the Yunqin vector symmetry, and Q1 will become the charge of the Yunqin axial symmetry. So we have these two U1 operators in the IR, sorry, in the UV, and they become the vector and axial operators in the IR. So we have some symmetry operators in the UV that from which this chiral symmetry is arising from. But the symmetry in the UV is very complicated. So Q0 and Q1 on the lattice, they don't commute with one another. And instead they generate this Onsager algebra. Now the Onsager algebra, Onsager wrote it out in the 40s to solve the Ising model. Okay? And that context, it arose because he was looking at the transfer matrix. He wasn't thinking about symmetries. And it's kind of funny to see the same algebraic structure arise in the simple fermionic model as symmetry. And the algebra itself, it's kind of straightforward. So you have these two different types of generators, Qn and Gn. The Q's fail to commute by these Gns. The Gns themselves commute with one another. And then the Qn and Gn fail to commute, but in a way that gives you a closed algebra and just spits out more. And you could look at the full Onsager algebra and ask, well, what happens when you restrict the IR? And this is a UV to IR symmetry map that you'll end up finding. So in the IR, Qn, if n is even, it'll go to QB. That tracks out with what we said earlier, right? Because Q0 went to QB. And if n is odd, it'll go to Qa. And then all the Gns will go to 0 as you take the IR limit. So what that implies, even in the UV, Q0 and Q1 don't commute. In the IR, they will. They'll give you the symmetry group of the vector and axial. Okay, so we see that the vector and axial symmetries can arise from some UV symmetries model. But we also know something, which is that the Dirac fermions vector and axial symmetries, they're anomalous. Yes.
So is there a generalization to n copy of fermion? You have a UN symmetry, UN vector, and UN axial, and write down on lattice your UN charges.
Yeah, so I'll actually in a few slides I'll show that because I'll start taking the n copy system, and we'll have some diagonal Onsagers, if that's what you mean.
So I'm not talking about a diagonal of the U1, just the UN, like figures.
UN.
Yeah.
Yeah, I haven't thought about it. You can easily write them down, but I haven't actually analyzed them all. Okay, good. Yeah, so as people probably know, the IR symmetry is anomalous. And its anomaly is an infinite order anomaly. And one easy way to see that is you just look at its inflow theory, some Chern-Simons theory, and there's no amount of stacking that will trivialize that inverter. So we know that the IR symmetry is anomalous, and it kind of begs the question, well, is the UV symmetry anomalous? But kind of have to ask, well, what even is an anomaly in a quantum lattice system? And there are more than one definition in the literature, and these definitions are not equivalent. They're very clearly not equivalent. There's examples where there's different answers. To me, this is one of the exciting things about working on anomalies in quantum lattice models right now. It's very active. It's not clear what the right structure is, and there's a lot of things to figure out. So in this talk, I'm going to take a perspective that I like, which is I want to think of an anomaly as a robust obstruction to a trivially symmetric gap space. Okay? Normally, for Toast anomalies, we view this as a consequence of the anomaly. Here, instead, I'm just going to view that as a definition. And one of the benefits of this perspective is that it avoids having to talk about gauging this. That Onsager symmetry that I just showed you, I have no idea how to, right? That's like a technical issue that shouldn't stop me from deriving constraints of the symmetry. And sometimes this definition of a lattice anomaly is called an LSM type anomaly. And there it gets its name from the Lipschitz-Mattis theorem, which is there's an obstruction to a trivially gap symmetric space. And it's well understood that these types of obstructions in lattice systems could flow to some Tufts anomaly. And lastly, I just want to note, while everything here is about the lattice, I kind of view the way we think about anomalies of non-invertible symmetries in quantum field theory in this way. There's, of course, this obstruction to a five-functive definition, but when you look at it in the PFP, it's very clear. Like you fix the symmetry boundary, you look at all of the other Lagrangian algebras, and if there's no magnetic Lagrangian algebra, there's no SPT, and that's what we call. So this is the perspective I'm taking in this talk. And under this definition of an anomaly in a quantum lattice system, the answer to this question is a yes. And it's pretty easy to prove the following. So you can prove that each symmetric local Hamiltonian will always take the following form. And it's a quadratic Hamiltonian, it's exactly solvable, and you could just prove that there's no Gn, choice of Gn's for which this Hamiltonian will have a unique gap ground state. And furthermore, as long as there's a single Gn that's non-zero, you can also easily show that this Hamiltonian is always gapless. So the Onsager symmetry implies a symmetry enforced gapless, which matches the consequences of the perturbative anomaly. Good. So let me make two remarks about this Hamiltonian. So sometimes people see this Hamiltonian and they see, oh, it's quadratic. I'm kind of bummed out. Yeah, I get that. So for one, there are interacting terms. They're all non-local. So locality is getting rid of the interacting terms in this specific Hilbert. That's the first thing I want to say. Another thing I want to say is you may say, oh, well, the Onsager symmetry group is so big. Of course, it's going to enforce things to be quadratic. That's not true either. So I'm just showing you the one particular Onsager symmetry group in one particular type of lattice system. There are other lattice systems whose Onsager symmetries do not enforce the theories to be free. And then furthermore, these theories, they're not exactly solvable. I don't know. They all have to deal with bosonic degrees of freedom, but I don't think that's. And the third thing I want to say is, along that same line, you may say, oh, well, it's such a powerful symmetry. Of course, it's going to enforce gaplessness. That's also not true. As we'll see in a moment, in the same Hilbert, well, in a slightly modified version of this Hilbert phase, there'll be an Onsager symmetry that, while it enforces things to be quadratic, it won't enforce gapless. Okay, good. Yes.
What are some sort of non-local interaction terms?
Good. So here's one way to generate them. Start with your favorite local term, and note that this Hamiltonian. Okay, it turns out that every Onsager symmetric Hamiltonian will also commute with Majorana translation. So take the A Majorana and translate it. So write down your favorite term in built out of A's and B's and start translating things. And you'll build something that spreads out over the entire system. And that'll be Onsager symmetric. Yeah, but it'll be incredibly novel.
Know what the Onsager symmetry is in IR?
No, I don't know how to solve the models. I don't even know the IR is. Okay, good. Okay, so in this staggered fermion Hamiltonian, the original Hamiltonian we considered a slide or two ago, we have this Onsager symmetry. It has some lattice anomaly. The Onsager symmetry obviously becomes the vector and axial symmetry in the IR, and the chiral anomaly in the IR we interpret as being matched by this Onsager symmetry anomaly. So those were all things that we worked out about 2 years ago. And then we've been very interested to have a more refined way of thinking about this anomaly. But the group is so complicated that the normal ways we think about characterizing anomalies usually fails. But what does work is this notion of order that we talked about earlier. And you can ask, well, what is the order of the Onsager symmetry? And this is especially tempting to ask because we know that in the IR it becomes a perturbative anomaly which has infinite range. And it turns out the order of the Onsager symmetries anomaly is 2, order 2. So what that means is that if I take my model, take a double copy of it, and preserve only the diagonal Onsager, there should be some symmetric term that gaps out there. And it's very easy to see that. So when I say the 2 copy system, now we have on each site 2 complex fermions. And by preserving the diagonal Onsager symmetry, what we're preserving is the Q0 built only out of the C1s, the Q0 built only out of the C2s, we take their sum. So we have Q0 diagonal and Q1 diagonal. And the following Hamiltonian here, it commutes with Q0 diagonal and Q1 diagonal. And it also has unique gap ground state. It's very easy to see that it has unique gap ground state. You can build new complex fermions built out of only the A's and only the B's. And then this is just a particle number term for those complexes. So what it means is that this diagonal Onsager symmetry is anomaly free, and therefore the original Onsager symmetry has an order 2. But then we ask, well, we really want to see an infinite order anomaly. That's kind of a bummer. Can we do something to the Onsager symmetry such that the symmetry's anomalies is enhanced to an infinite order anomaly?
First question.
Yeah.
So what happens if you track the chip to go to the IR? So for instance, if you have a free fermion, 2 copies of free fermion, and then on the lattice you can gap it out while preserving the Onsager, diagonal Onsager.
Yeah, good.
And if you, because the Hamiltonian is just a quadratic, so you should be able to explicitly track what happens in the low energies. And
Yes.
in the low energy, the system should also be gapped, but it still preserves the U1. Should still preserve the U1 factor and the U1 axis.
Yeah, so
So
when you say track it in the IR, you of course need to specify which Hamiltonian. I'm assuming what you mean is you take the staggered fermion Hamiltonian and you deform it by this term.
that's right.
Good. Yeah, you can track in the IR, and this becomes some chemical potential term in the IR. And the chemical potential just shifts where the gapless mode is, but it actually won't gap anything. Yeah. Okay, good. So one way to increase the order of an anomaly is to add more symmetries. And the symmetry we're going to add here to try to enhance the anomaly's order is some lattice CPT symmetry. And this is very natural from the QFT perspective. We know that the Dirac fermion QFT already has a CPT symmetry in the IR anyways. It's not so much natural from the lattice model perspective, though. I think that's all. Good. So this is the lattice CPT symmetry we're going to consider. We're going to consider this following anti-unitary operator pi. It's going to square root 1. Okay, it's anti-unitary, so it sends I to minus I. And it does a link-centered reflection of the complex fermions, and also hits it with a dagger. So this is some Z2 anti-unitary reflection. And it's easy to check that it's also symmetry of the staggered fermion Hamiltonian. Okay. And it's also easy to check that in the IR, this pi operator becomes the CPT symmetry operator of the Dirac fermion QFT. So because it's some anti-unitary reflection in the UV that becomes a CPT operator in the IR, we'll refer to this as a lattice CPT symmetry operator, and we'll start to denote this group by Z2 with a CPT above. Okay. So we know that the staggered fermion has this lattice CPT symmetry. We also know it has the Onsager symmetry, and you can ask, what is their interplay? And the interplay is pretty straightforward. So pi acts on the Onsager charges. In particular, pi sends Qn to minus Q minus n, and it just commutes with the GMs. Okay, so it forms some semi-direct product. And in the IR, the staggered fermion Hamiltonian, this semi-direct product group will go to the U1b, U1a symmetry times the Z2CP. By the Coleman-Mandela theorem, it's important that the semi-direct product goes away in the IR, and that's indeed what happens. And the precise relation that underlies this UV to IR symmetry map is the following. So, okay, remember in the IR, G becomes 0, so nothing interesting happens here. So it's all about what's happening over here. So in the IR when n is even, Qn will go to V, Q minus n will also go to V. So this just becomes the charge conjugation of QV. And similarly, when n is odd, we'll have this become the charge conjugation of Q. So that's giving rise to C in the CP. Okay, so now we're going to enforce this Onsager semi-direct Z2 CPT symmetry. And this symmetry is obviously anomalous, right? The Onsager symmetry is anomalous. Adding additional symmetry is not going to get rid of the anomaly. But the question is, well, what is this order now? And using the same exact method we just used for the order 2 case, we can show that it's order infinity. What, of course, that means is that if you take this n copy system and only preserve the diagonal symmetry of Onsager semi-direct CPT, that n copy system will always be will never have a unique gap ground state, regardless of what n. So the n copy system now on each site will have n complex fermions, and we'll have a big diagonal symmetry generated by the following. Here, pi diag, it acts on each complex fermion as the respective pi of that complex fermion. And in this context, you can prove, again, that the most general local symmetric Hamiltonian is quadratic and takes this form. Now, if you didn't enforce CPT, you would not have this constraint on Gn. And without that constraint on Gn, taking big N to be 2, there's some gap term that gets rid of it. But that term does not obey this condition. And with this condition, you can show that for all big N, this Hamiltonian is always gapless. Okay. So it never has unique gap ground state. And therefore the Onsager times each symmetry has an infinite order. Yeah, okay.
I don't know what you over that.
Yeah, there is. So we also wrote about that in the paper. I'm not going to talk about it in this talk. I don't know of an easy way to communicate what the inflow theory is. It's some lattice model. It looks similar to, it has some foliation structure, but I don't have a good way to characterize it. But in the paper, we do have this inflow theory perspective, and you can see the anomalies order through this inflow theory perspective.
The reason I'm asking is that I struggle in understanding. I guess that here there is no mix up between the side algebra, right? It's just that, of course, CPT makes the anomaly of the side algebra. It's not that we're modifying the anomaly. The anomaly is still the same.
I don't know what it means for the anomaly to be the same. It has a different order, so that doesn't sound like it's the same anomaly.
Yeah, that's why I'm asking the inflow effect, whether like the inflow or you enforce CPT is the same inflow.
Yeah, we can talk more about it after. I'll just say quickly. So when I say we have an inflow theory, I mean like quite literally. We have like explicit models for the inflow. And with or without CPT, the inflow theories are the same. But enforcing CPT changes the order of the SPT, of the inflow theory. Yeah, but I'll be happy to talk about it more. Yes, please.
No, the one you have keep up. And we got was the anomalies of the group that you broke down the system.
While preserving the vectored axial? I don't know. What I do know, though, is if you take the 2 copy system of the Dirac fermion and you give up the Lorentz invariance, then you could gap it out. Which is very suggestive because the Onsager symmetry had an order 2 anomaly before we enforced like things that come from the Lorentz invariance. And I think you get Alice on. Yeah. Yeah.
For example, we have, your finite group D, it only is multiplied H3.
Yeah. That's a great question, and I have no idea. But I think that's one of the reasons it's so exciting. There's a lot of things to do.
And it's not quite related to a central extension of the D into another form.
I don't know. Yeah, I don't know. Okay, good. So, okay, so let's just recap what we just showed, and then I'm gonna. So we started off with this very complicated UV Onsager symmetry, and its anomaly order is 2. And if we look at the staggered fermion model, the Onsager symmetry in that model, it becomes the normal vector and axial symmetries, and that has an infinite order anomaly. And what we just did is we added an additional symmetry on the lattice scale. And for this model, that didn't change what the IR anomalies order was. And it didn't change what the IR symmetries was. Like this CBT just comes along for the ride. But it does change what the UV anomalies order is. And it changes it to match the IR anomalies. And then you can start to dream. Like maybe if I add CPT symmetry, I can take some lattice anomaly orders and kind of increase them to that in the IR. And there's other examples of this too. So for one, you can take the Heisenberg chain, and the Heisenberg chain has a translation symmetry. And it's well known that in the IR, that translation symmetry becomes some internal Z2 symmetry that's anomalous. So this is the case where the translation symmetry is anomaly free. It has order 1. The IR symmetry has an anomaly that's order 2. And then you can enforce a lattice CPT symmetry. And that enhances the UV anomalies order, the 2. And similar in the Katai chain, you can start with the Majorana translations. This has an order 2 anomaly involving Majorana translations and fermion number parity. And in the IR, this goes to an order 8 anomaly. And then if you go back to the UV model and you enforce a lattice CPT symmetry, the UV's anomaly order gets enhanced to order 8, right? And these are the examples I know that are in the literature, but I also know there's more examples where you enforce lattice CPT and you get something to match its IR results that are not published. So I think there's a lot of cool things to do based off of this, and I think that suggests there could be something deep underlying. The first obvious question is, what is the role of CPT, or more generally CRT symmetry, in quantum lattice models? There we just saw that enforcing the CPT in 1 plus 1D enhances the anomalies order to match that of the QFT. And there's some also interesting results in the context of invertible phases. There's this paper by Ogata where she showed that if you take some index classifying 2 plus 1D fermionic SPTs, it only matches the continuum answer if you enforce a CPT. And there's another paper by Nikita that shows that if you take some invertible states, there's always some reference state that has a CRT. But then there's more less ambitious questions that I think come from this as well. So in this talk, I never talked about ancillas, but ancillas are important. We want to say, oh, if I have some anomaly, some obstruction to a tributary gap phase, and I just tweak the local Hilbert space, I don't want that to go away. And that's what adding ancillas basically does. And in the paper, we have some preliminary results where we look at a large class of ancillas and show the anomaly is robust to adding those. But it really calls for more systematic investigation of how ancillas affect. And what makes it so tricky is the Onsager symmetry group is infinite dimensional V group. There is no on-site symmetry operators with finite dimensional Hilbert space for that. And the way we normally think about ancillas is by using on-site ancillas that are finite dimensional. So I think this really calls for like a generalization of how we think about ancillas. Okay, and the last interesting direction that I want to mention is everything was in 1 plus 1D, but Onsager symmetry is also arising greater than 1 plus 1D. And there's some generalized versions of Onsager symmetries too. And in those greater than 1 plus 1D cases, they've also been shown to be related to QFT anomaly. So there's examples in 2 plus 1D that you can have some parity anomaly in the IR come from some anomalous Onsager symmetry in the UV. And similarly, in 3 plus 1D, you can have Witten's SU2 anomaly come from some Onsager symmetry. And if you know this story about Fermi surfaces and anomalous LE1 symmetry, there's also a relationship between Onsager symmetries and that in any dimension variant. I think it'd be interesting to go through these higher dimensional examples, add some lattice CRT symmetry, and look at its order compared to in the IR instance. So thank you all for your attention, and please ask more questions.
Something about the anomaly cancellation story as well as something about the neutral place.
Yeah. So you could take the on-target charges, add them in the right way you want to. The thing is though, when you add these charges, they don't commute, you won't get a U1 symmetry out. So yeah, so it seems like it's a big obstacle to taking this formalism and applying it for like things like 3.5.
Curious also to get this piece maybe over its status. Can you propose something weaker than PT? Or leading the way?
Yeah.
Halfway down the argument.
I don't see any reason why you couldn't. So suppose like we start with an order 2 anomaly, we want to shoot for an order 8 anomaly, and you impose like some middle symmetry that gets you to order 4, and then you impose some more symmetry that gets you to order 8. I don't know any examples like that, but I don't see any reason why that can
In our view, though, you expect that it should be this starting from order 2 and then order 8. You expect it to be order 2 all the way until exactly the IR.
Yeah, I think it depends on the details of the RGs, but I've really been thinking only about the extreme points. You can, I guess, imagine some midway point where something a little bit discontinuous happens, and you have like, you hit some like energy below it, there's like some pair creation, and you get some new symmetry instantly. Maybe that could induce something like you're suggesting, but I haven't thought about it, but it sounds pretty cool. Yeah, you can do that. I don't think we want to do that. When you say transform trivially under the symmetry, you could definitely do that. I don't think that would be the right. Oh, I see. Okay. Yeah, you could do that, and that can allow you to build interacting terms. Absolutely. Yeah.
But then there's issue. You got a lot of interaction question, and you do something. Yeah, for sure.
Okay, let me take.
There's no, you might not allow, so.
Yeah, okay, sorry, let me take back what I said. The Onsager symmetry acts in a very complicated way. And I think if you just naively, okay, let's say you add like a second species of fermion on each site, and it doesn't get transformed by the Onsager symmetry, and you just multiply those fermions by the original ones. I think that would give you something that won't end up being symmetric in the end, or it'll have to be non-local. This because of how complicated the Onsager symmetry acts. Yes, it has like some of the elements of the Onsager symmetry has this glider effect where things get translated. Yeah, so I think that would be an issue with what you're suggesting. Yeah.
And another thing is that we are stacking several copies of layers. And you assign to each layer means you combine inside a chart with different location. That's pretty cool.
Yeah, you could do that. And like for example, one thing you can show. Well, one thing you can show is so the Onsager symmetry generated by Q0 Q1 with the CPT generated by pi. You could stack it with something that is Q0 minus Q1 and pi. And the stack system will be a nominal. So this is like the inverse of this. And that's expected because that's also how it works in the continuum.
So kind of still has a fact like tools.
In this context, yes, you definitely could. Yeah. Yeah, there's nothing happening. Yeah, I think it's, well, what do you mean by well defined? So the
yeah. The order unchanged.
Yeah, so yeah, when I sit in this preliminary result point, when I say that the anomaly is robust, the order is also robust to all the ancillas we consider. And we considered an infinite number of ancillas. We just consider some general class of ancillas, and there's infinitely many of them. But we didn't consider every possible ancilla that we can think of. But for all the ones we checked, the order is maintained under adding ancillas, both the order 2 and the infinite order case.
All right, I think this is good to stop. Let's thank Sal again. We'll come back in 10 minutes.